So our next speakers are Xavier Généreux and Jannis Limperg, who are going to tell us about efficient forward reasoning for Aesop.
Okay, thank you. So everyone can hear me?
Yes?
Okay, super. So thank you for the organizer for the opportunity. So today I'll be talking about a project I've been working on with Jannis, efficient forward reasoning for Aesop. And so the plan for today is I'll be beginning by kind of catching everyone up with what is Aesop, and how does forward reasoning tie into that, and then Jannis will take over and explain how to do this efficiently. And yeah, so let's build up to what is forward reasoning for Aesop. So what do we mean by forward and backward reasoning? In backward reasoning, to prove a goal, we reduce it to simpler goals. So in Lean, you have something like the apply tactic, which does exactly that. And here the work is really on the goal's target. On the opposite, for forward reasoning, here from given facts, you deduce new facts. And in Lean, that looks like have or obtain. And here the work is being done on the hypotheses. And yeah, so for the ones that don't know, what Aesop is, it's a tactic for customizable proof search. It applies user-specific rules to goals, and rules are really arbitrary tactics. And finally, if a rule does not fully solve a goal, it will produce sub-goals that Aesop will try to prove recursively. So now I said that Aesop rules are arbitrary tactics that you put in a rule set. But what do these look like in practice? In practice, they look like applications of theorems, and Aesop provides convenient syntax, what we call rule builders, for creating rules from theorem. And this is where forward and backwards reasoning ties in. So in the rule builder, you kind of have to specify how do you want Aesop to use the theorem. So do you want it to use it as an apply rule so that it uses it backwards, or as a forward rule if you wanted to use it forward? Okay, and now the challenge is you have your rule set with the theorems you would like Aesop to try, but kind of the difficulty is, okay, is this rule the backwards rule, or should I make it as a forward rule? So we're going to look at a couple lemmas and try to think a little bit how we can go about this. So for this lemma here, we have this very basic lemma. If the proposition A and B are true, then so is A and B. And if we look at the premises here, A and B, this is what the forward rule would look at. And these are quite general, right? It's just two propositions in the context. It's not really interesting as a forward rule because it would get applied way too often, and it would also not give you a lot of interesting information. It would just add as a hypothesis A and B to the context as well. However, as a backward rule, it's much more interesting because now you have this specific conjunct which is typed, and so if it appears as a target of your goal, then you know that it might be interesting to apply this, and it will mimic the behavior of like constructor does. And yeah, and this is also a lemma that's in Aesop basic rule set actually as a backwards rule. So we can look at another example. So this is the transitivity of the less or equal relation. Here, is it interesting as a backwards rule? Well, you have this result of the rule A less than C. So Aesop would try this, if it was a backwards rule, it would try on any goal which is a less or equal. So this happens quite a lot, I imagine, and it's not really desirable to try this every time that you have a less or equal target. As a forwards rule, it's a bit more specific. You need the two hypotheses, and also you need this B to be consistent, right? You have this equality that you need to maintain for it to be applied. So I argue that this is more specific. You have more information in the premises, so it makes more sense as a forward rule. It would be worth to try it as a forward rule. Another example you can have this lemma which says that if you have a Cauchy sequence in a complete space, then the sequence will converge. As a backwards rule, well, it's kind of generic, right? You don't have a very specific target, you just have series converge. But as a forwards rule, here the premises are a bit more specific. You have the Cauchy sequence, you have the complete space, so it can be interesting to add to your context that the sequence will converge. And as a final example, now we kind of get the rhythm. We look at the result of the rule, right? And maybe I'll read the theorem. What it says is if you have a closed set and a converging sequence, such that for all n, the members of this sequence are in the set, then the limit will also be in the set. And as a backwards rule, right, it's very generic. You just have membership of a set. So maybe we're not even talking about sequences. And as a backwards rule, it would get tried. But as a forward rule, now you're a bit more strict. You're asking for much more specific information. In particular, you're asking the sequence to be convergent, also looking for a closed set. So it makes, I think, more sense to try this as a forward rule. But this is very idealistic, right? So in practice, it can be different, but this is kind of the general idea of which rule you kind of want to try for forwards and backwards reasoning. And lastly, I want to end this kind of intro with a disclaimer by saying that backwards rule try in some way harder. The thing is, forward rule will never succeed if one of the premise of the rule is missing from the context. However, here, backwards rule may succeed if they get applied because it would try recursively to prove the premises. So even in some cases, it can be interesting to try it as a backwards rule, even if you have more information in the premises. Lastly, though, there's still some options for forward rules, which we call the immediate options, that kind of make it possible for forward rules to be tasked and have the premises be proved later. So there's still some hope to use forward rules sometimes, but this needs to be kept in mind.
All right. At this point, I'll take over and I'll talk about how we implement this. Because all this functionality has been available in Aesop pretty much since its inception. It's not used a lot in MathLib. I think we should probably try to use it more, or at least experiment with using it more. For example, to establish facts that might be relevant for omega or for linearith, that kind of thing. But perhaps one reason it wasn't used very much is that up to very recently, it was extremely inefficient. And so possibly if people tried to use it, they might have run into performance difficulties and then stopped using it. Well, over the last year, Xavier and I have worked on a much more efficient implementation, and I'll talk about how exactly that works and what the effect of it is. So this is going to be my running example for this part of the talk. We are going to assume that we have some relation R on the natural numbers. We will assume that this relation is transitive. We want to use this transitivity as a forward rule, like you saw in Xavier's part already. And we have this little goal here that says that R holds between 300, 301, 301, 302, 302, 303. And we want the full transitivity chain. So we want to go from 300 to 303. Okay. Now, to say why it was so slow, let me first talk a little bit about the naive algorithm that was what I initially implemented in Aesop. So the naive algorithm was very simple. Basically, it would take the lemma, and if it thought that the lemma was possibly applicable, it would start to look for basically instantiations of the premises of the lemma, and it would go back to front for technical reasons. So it will first try to find an instantiation for this R, Y, Z. And to find an instantiation, we'll go through all the hypotheses, starting with the first one. So it would see, does R, Y, Z match R 300, 301? It does. And we get this kind of substitution where Y is 300, Z is 301. Okay, having found this successful match, we would go on to the next premise of the rule, Rxy. And again, we would match it against all the hypotheses, right? So we would match against R300, 301. We will get a substitution. So that's fine. However, the Y here is a different one than before. Here we have 300. Here we have 301. So that doesn't work. Okay, we try a different hypothesis. We try H2, 301, 302. It matches, but the Y is 302. That also doesn't help us. We try a different one, 303. Also doesn't help us. Okay, so we're not going to go anywhere here. We therefore try this RYZ against the second hypothesis, H2, and we get a match. We again try to find something for RXY. We match it against the first hypothesis, and hooray, we are finally getting somewhere, because here we have Y301 in both cases. So this is a full match for this rule, and we can add a new hypothesis, H4, going from 300 to 302. Okay, so the rule has produced a new goal with an additional hypothesis down here, and we continue to execute Aesop. And on this new goal, Aesop starts afresh. Right, so basically it tries to run this transitivity rule again. Therefore, it tries to match RYZ against the first hypothesis again. It tries a bunch of possibilities. They all don't work. It matches it against the second hypothesis. It tries a bunch of hypotheses. It finds the thing that we already found. And then, it continues like this. And you can probably see why this is inefficient. The central issue is that this algorithm is stateless. So basically, it doesn't remember any information that it got from any of the previous goals. And this leads to a ton of duplicate work. And the essential contribution of this talk and of the work that this talk is based on is that we have developed an efficient way to cache the work done for one goal in what we call a forward reasoning state, and we reuse the state for sub-goals, with the essential assumption being that if you have an initial goal, you run an Aesop rule on this goal, and you consider the child goals produced by the rule, most likely the contexts, so the hypothesis of these goals, are going to be quite similar between the parent goal and the child goals, right? Because the Aesop rule, like maybe it added one hypothesis, or maybe it removed one hypothesis, or maybe it added a couple, but more likely than not, most of the context is stable between these goals. And so we should be able to reuse a lot of the work that we did on the parent goal for the child goals. Okay, so basically that means that we want an interface looking like this. So we want this state data structure, and we want to be able to add hypotheses to it, right? So if the child goal has one more hypothesis than the parent goal, we want to be able to add that, or if it has multiple, we should be able to call this method multiple times, and then it'll add all of them. And that should update the state in some way. And if we have some new hypothesis, possibly it becomes possible to apply a forward rule that was not applicable before. So adding a hypothesis may also give us some new hypothesis that we should add to the goal. And we should be able to erase hypotheses because the child goal might also have fewer hypotheses than the parent goal. I'll not really talk about that. It's also implemented, obviously, but it's not really the interesting part of this work. Okay, so the question is now, how do we implement the state and this functionality? And to talk about that, I'll introduce a little bit of terminology about forward rules. So let's consider again the transitivity rule that we've seen a couple of times already. And we first notice that some of the premises of this rule, namely x, y, z, are already determined if we have a match for these premises P1 and P2. Right, so if we match P1 against some hypothesis, it's going to give us some specific x and some specific y, and that already determines these premises x and y here. Similarly, if we match P2, it'll determine z for us. So we don't really need to care about these premises explicitly, and we only look for matches for P1 and P2. And we call P1 and P2 the slots of this transitivity rule. And we say that they are connected by a shared variable, namely y. That's just a variable that appears in both premises. Here we only have one. In general, of course, you can have many or zero sometimes. Okay, and what we are ultimately after is a complete match for the rule, which is a substitution for each premise that is a slot. We identify slots by numbers, right? So we have a substitution for slot 1 and slot 2 here. And the instantiations for these must obey some restrictions. Namely, first, this T here for slot 1 must actually match the type of slot 1. The U for slot 2 must actually match the type for slot 2. And the shared variables induce some equality constraints. So this B needs to be the same as this C down here. And in kind of on the way to a complete match, we will also consider partial matches, which are substitutions that obey the same restrictions, but they only have assignments for some non-empty prefix of the slots. So here we might have a partial match that has some value for slot 1, but not for slot 2. Based on that, we now build a rule state, and this kind of forward state that remembers work that was already done then contains a bunch of rule states, one for each forward rule. And each rule state contains two maps, capital H, capital M, with the same domain and slightly different codomains. So in the domain of the maps, we always have a slot index. So here it's either going to be 1 or 2. We have a shared variable, and we have a lean expression. I'm going to explain in a moment what this actually is. And the hypothesis map then maps to sets of hypotheses. The match map maps to sets of matches. And so what this is for, I think, will become clear now, hopefully, when we look at an example of how a hypothesis is added to the state. So we have the usual example, the running example, and we add two hypotheses. For the sake of the example, I've switched them, so I'll consider H2 first. Yeah, so when we get kind of a new hypothesis, so a hypothesis that is in the child goal but has not been in any parent goal, then what we do first is we add it to this hypothesis map. And we add it in a specific place. Namely, we notice that H2 matches slot 1. So we add it in as a slot 1 thing. And we notice that the shared variable y is assigned to 302 when we match H2 against slot 1. So we added with 1 shared variable y, instantiation 302. Here we create the set containing only H2 for the moment. Now, anytime that we add a hypothesis for slot 1, we can also consider it as a partial match with just one hypothesis in it. So we also add it to the match map with exactly the right, the same path here. And we consider the partial match mapping slot 1 to H2. And we can also match H2 against slot 2 of the rule, which is this RYZ up here. So we also inserted at slot 2 with the shared variable y now being instantiated with 301 here, right? Because if we match H2 against this guy, y becomes 301. Again, no. Okay, sorry, I messed that up. So now the question is, basically, whenever we get a hypothesis in a slot above 1, we should think about, can we extend any of the partial matches that we've already collected with this new hypothesis? So basically, can we make progress on some of the forward rules that we've tried to apply? And in this case, so we would be looking for matches in slot 1, right? Because the matches in slot 1 are the ones that we can possibly extend with a slot 2 hypothesis, such that y is instantiated with 301, because the matches that we consider need to be kind of consistent on the shared variable y. So we look in this map, slot 1 shared variable y 301. Unfortunately, there's nothing, so we can't extend anything. Okay, sure. Now, we are done with H2. Let's consider H1. So first, we can again put H1 into the kind of hypothesis map. Now here, if we match H1 against slot 1, we're going to have y equals 301. And we add a corresponding match in slot 1 as well. But now this match is more interesting, because whenever we add a match here, we should also consider, can we immediately extend this match with some of the hypotheses that we already know to exist in our context? So in this case, we have a match here that wants a hypothesis in slot 2, shared variable y instantiated with 301. And lo and behold, we have a hypothesis H2 here. And so we can extend this match and make a bigger match that has both slots filled. And since the rule only has 2 slots, we are actually done at this point, and we have discovered a new hypothesis. I should quickly mention here that this is kind of a degenerate example because we only have one shared variable. If we had multiple of them, then we would basically have to go through the maps multiple times and look for the intersection of the hypothesis of matches that are consistent with all the shared variables that are relevant at that point. But you can probably imagine how this would go. Okay. Right, so we get a new goal, right? We've discovered a new hypothesis, H3, that goes from 300 to 302. And here's kind of the crucial thing about this new approach. So when we want to work on this new goal, and we want to check whether H3 now enables more forward rules, we can reuse the entire state that we constructed previously, containing all the partial matches that are enabled by H1 and H2, because these hypotheses are still available in the context, and we just need to add H3. So the whole thing has become essentially incremental, and we have to do very little additional work when adding a new hypothesis. Okay, here's the kind of entire algorithm. I'll skip this for time reasons, but I just added it kind of for viewing later. And now the question, of course, is does this actually work? Like, is it actually more efficient? And the answer is that at least on this specific example, it is vastly more efficient. So here's a little benchmark that we set up. It's the same as before, but we add n instead of just 3 of these hypotheses that continue the transitivity chain. And here are the results of doing this. So in this table, n is the number of hypotheses that we had initially. K is the number of hypotheses that that Aesop has to add. So the number of hypotheses added by forward reasoning. T old is the time that it took the old implementation. T new is the time that it took the new implementation. And you can see that the old implementation already struggled mightily on my laptop with 20 initial hypotheses. Here it needs to add 190 new hypotheses, and it took 18 minutes to do so, which is definitely excessive. And for 30 and 40 hypotheses, I didn't bother trying. The new implementation stays in the millisecond range, even if we go up to 40 hypotheses, where it adds 780 hypotheses to the local context, which is a point at which rendering the info view in VS Code and Emacs becomes a little bit slow already. But yeah, so it scales much better on this particular example, and also on probably most other examples. There are certain cases where the old implementation has some kind of behavior that makes it perform better. I believe that these are largely edge cases, but we haven't done the full evaluation yet, so I can't say anything definitive. But based on these numbers, I'm quite certain that we're going to be faster overall. All right, that's it from the two of us. We've left some time for questions. I hope you actually have any.
Thank you very much.